Alrighty. So we're looking at directional derivatives and then the concept of the gradient vector today. Both are hugely important, frees us up from being stuck to just differentiating with respect to the coordinate axes. We're going to start to look at what does it mean to find the rate of change in a function when I move in a different direction than just in the x or the y or the z direction. And from that idea emerges this thing called the gradient, which you will learn about. And you'll see that this is an ingredient in, that's kind of confusing, ingredient and gradient, but it's an ingredient in a lot of important theorems moving forward. Some of the biggest ideas that we'll cover towards the end of the course involve the gradient to some degree. And it's not a super intuitive thing, but it is super interesting and very useful. So, with that being said, I'll open up with some kind of a motivation, intuitive understanding of a directional derivative, and then we'll get into the notation and working through some examples. So I'm going to make up a map. This is not real, okay? So we've got Rochester and Canandaigua. And let's say we've got a heat map or a temperature map. Okay, and what this is doing is mapping out the contour lines of the different temperatures in the regions around. So let's say, around Rochester, we got a 32 degrees, and then as we move out, something like this, 35 degrees on this particular day. Let's go a little bit more orange. Something like this, maybe at 38 degrees. And then a roasty 41 degrees. So based on our understanding of partial derivatives, right, we could ask and answer simple questions like, if I moved north or south, how is the temperature going to change, right? Or if I moved from left to right, talking about the partial with respect to x, how's the temperature z going to change? And we can come up with that answer. But in the real world, so to speak, I might want to say, well, if I make a move from Rochester to Canandaigua, right, if that's my direction of motion, what's the resulting rate of change in the temperature, right? So this is the idea behind the directional derivative. I'm not moving just up, just down, just left, just right. Moving in a particular direction, how is the output going to change at an instantaneous rate, right? Can we do that? So this is the idea. And we can do that. And I'll actually, while we're here, let's explore what do you think intuitively we would do to generate that idea, to generate that quantity or that rate, to measure how much the temperature is changing when I move in the direction from Rochester to Canandaigua. I saw in the chat maybe an angle, so sine or cosine, right? We could definitely break it into an angle. So that's telling us how far off the x-axis we are.
Apply like a direction vector to partials?
Yes. That's what we're doing for sure. So apply a direction vector to partials. So could you unpack that a little bit, because I think you're onto it.
So like use the direction I don't know where you go from there, but that seems like a good start.
No, that's good. You definitely want to use the direction of the direction vector, and you're pointing to it maybe being a unit is a good idea, right? Because we don't want the magnitude of the direction vector to mess with the rate, right? If we're just talking about moving from Rochester toward Canandaigua, not how far, right? But just preserving that direction only. And then, yeah, how do we use the partial derivatives? Well, we would kind of weight them, right? Um, so in a way, if we said we're moving 45 degrees this direction, or the same direction over as down, right? Then we would want to weight the partial derivatives equally, right? And if and sum them up, and that would give me the total change. And if I was maybe heading more in the negative y direction, well, I'd want to weight the partial with respect to y a little bit more than I would the x, right? So we can break it into its components, and those components would be related to the partials. So yes, we're definitely on to that intuition. And and again, that idea offered in the chat about having an angle, so sine or cosine get involved, that's definitely related to the x and y components, right? So this is correct. So let's move into the definition of this thing. And I'll sketch out what this means in the general case. Directional derivative of f, a function of x and y, in the direction of a unit vector u, which will give components a and b, is, and this is if the limit exists, we'd say this is derivative in the direction of u of f of x, y. And so I'll give you the limit definition, which you might be able to parse, but I think the sketch really helps this. So f of x plus ha, y plus hb, minus f of xy, all over h. And that's if the limit exists. So this is the directional derivative. So what do we mean when we say this? Well, let's pretend we've got some surface. I'm actually going to make this a little bit bigger. Got some region of a surface here. And so let's say at a given point, so here's my z equals f of xy. So let's let p naught be some point x naught, y naught in the plane. We'll call that p naught here. So if we think about projecting this up to the surface, right, and let's even call this one p naught prime, and we'll let p naught be x naught, y naught, f of x naught, y naught. So just the point on the surface for this particular set of coordinates. here's P naught, here's P naught prime. If we think about starting at this point and moving in the direction of some direction vector, some unit vector u, and we want to talk about the instantaneous rate of change of the height of the surface, well, we'd be talking about this tangent line over the top of it, right, that has the same direction as u. These should look parallel. Since it's sloped, it looks like they're not, but this tangent line t and u are both pointing in the same direction. Close this here. And so what we're doing with this limit definition is moving out to some q, right, out here on the tangent line. Let me back this up a little bit. Here's some like little q prime. And we're going to cinch back, having it turn from a secant line to a tangent line, just like we would in single variable. Okay. Instead, we're cutting across this surface. We're living inside the plane that slices along u, right? And we're taking the tangent line from the limit of the secant lines, moving along the curve that intersects. So you could think of this being like a plane. I'm just going to draw this temporarily. A plane that slices through in this direction. And so it's going to intersect along some curve, and we're going to move along that curve and make the limit of the secant lines become the tangent line. So what's the important part is down here, and I'm going to zoom in on this. And what this really looks like at the point P prime here's my direction vector u, which has components here h times a and h times b. If this is scaled up between this and some q prime. H is that shrink wrapper, right, that we let go to 0. A and B are just the components of the unit vector, the direction that it's pointing in. These are scaling them. So we shrink these down, and what's going to happen? We're going to move to be sitting right on top of this point. Okay. We let h go to 0. Secant line becomes tangent. So if we take a look at this definition, right, this is starting at some point, any point x, y, scooting over in the direction of u, right? This looks like vector addition, right? Plus HA plus HB. So this much in the x direction, this much in the y direction. So we're scooting over a little bit. How much? Just by h. Finding the difference between the two, and then letting h go to 0 so it snaps into just kissing the surface right at that point. So that's what this definition means. Now, this is pretty cumbersome to use. Okay, just like the limit definition with finding the derivatives. We only really did it with, quadratics, and then we never really took it much farther than that, because it is a pain. There are theorems that make it easier, and we're going to use those instead. But this is a nice definitional understanding to have. All right. So with this, and hopefully a bit more of a geometric sense behind it, we can look at this theorem which says if f is differentiable, right, which means it has continuous partial derivatives, then f has a derivative in any direction u. And what that tells us is that, well, actually, let me unpack this one a little bit. So I'll come at it from this perspective. For a point x naught, y naught with u having these components. And we have f of x, y differentiable. What we can do is so I'm going to be a little creative and show us by making the substitution that we can have a more workable form for the directional derivative. Okay, so that's my motivation here. All right. So if I take some g of z, and I say I'm going to let u be equal to my function so that x is equal to x naught plus az, so x and y, this is not an equal sign here, and y is some y naught plus bz. So now I've made x and y functions of z. So I'm on the surface, and these coordinates are being dictated to me by the direction vector, right? So I'm making this little substitution so that what I can do is look at g prime of z. Because when I do this, I use the chain rule. I say, well, this is the derivative of g with respect to z, which is really what? Well, that's the partial of f with respect to x times dx dz plus the partial of f with respect to y times dy dz. And so what does that get me? Well, what is this and this? This is the partial derivative with respect to f, partial derivative with respect to y of f. And then this dx dz, if we take a look up here, this partial, or this derivative rather, is just a, and this derivative is just b. So this becomes the partial derivative of f with respect to x times b plus the times a, plus the partial with respect to y times b. Oh. So that's some g prime of z. And now what we can notice here is that this is really, well, one following thought here, which is that if we let z be 0, we're going to get the derivative at the point. We're going to get the derivative in the direction of u at the point. Right? If z is 0, each of these drops to x naught and y naught. This becomes the partial at x naught, y naught, a. Oh, why is this ab here? There's an error here, guys. This should be x naught, y naught. Did you guys catch that? No, just x and y. All right, let's take a step back. For this line right here, I goofed. We're going to fix it. So we took the derivative of f with respect to x. That's the partial. Partial derivative of y with respect to y. That's the partial y at x and y. This was the coordinates that got goofed up right there in red. Okay. And then the derivative of x with respect to z is a. Derivative of y with respect to z was b, and that came from here, right? Because these are just linear functions of z, this kind of dummy variable we threw in. So where do the x naughts and y naughts come from, Mally? Kept dropping those in everywhere. Well, they come because when I let z go to 0, okay, I'm going to pull up this thing here too quickly. When we let z go to 0, what happens? This x coordinate becomes just x naught. This y coordinate becomes just y naught. Okay, so let you copy that down for a moment. My note here got clipped, so I'm just trying to recover this. Hey. So essentially we can draw a straight line back from this g of z to being the derivative of u, the derivative in the direction of u of f of xy. Okay, so this is nice because we have this at the point and we have this at any point xy. Now, why did we do that? To show you that there's another way to drive at this thing. The main point of this is to have this result that the derivative in the direction of u can be broken into how we weight the partial derivatives in the x and y direction. Okay, a is how much we do it in the x, b is how much we do it in the y. So let's use this because that got a little fuddled, and it should help drive it home what this is really for. So, and then I'll show you this does extend to our Rn. So, example. we're going to do a three-dimensional. So find the direction vector, the directional derivative in the direction of u for f of x, y, z, where f is given by this guy. X squared z plus y cubed z squared minus xyz. In the direction of this vector v, negative 1, 0, 3. So, a couple things. We're going to use this theorem that we had above, which tells us not that, but this here, and we didn't write it out, that right, this is what we defined g to be, but we should state it explicitly. This gives us the directional derivative. Okay. So, in the direction of u, but here v, negative 1, 0, 3, how is this thing changing? Well, a couple things we got to remember. The derivative needs to be taken in the direction of a unit vector, right? So the first thing you have to do is make sure that you have a unit vector. If you don't have a unit vector, it's like changing the scaling of the x-axis when you were taking the derivative before. It's going to change how you're measuring that rate, okay? So it needs to be a unit measure. So if it's not a unit vector, we can easily just make it one, right? Preserve the direction, but not the magnitude. So we'll say, check that it's a unit vector. Is this one a unit vector? No, you can see that, right, magnitude of v is what? 1 squared plus 0 squared plus 3 squared, which is radical 10. So then we can just scale everything down, right? Divide all the components by radical 10, then we get ourselves a unit vector. That's the easy way to do it, right? So we'll let u be v over magnitude of v, which is then negative 1 over radical 10, 0, 3 over radical 10. Okay. So now we've got the direction preserved. And so what we have from above is that the derivative in the direction of u is the partial with respect to x times a plus the partial with respect to y times b plus the partial with respect to z times c here, because we have a three-dimensional vector. And again, doesn't this make sense? We're weighting how much the partial in each direction with the coordinates given by the direction vector. So we'll need all these partials. So f sub x is what? 2xz minus yz. And that's coming up to here. Partial with respect to y, 3y squared z squared minus xz. And there's a z term in each one, so this is going to be x squared minus or plus 2y cubed z minus xy. And so we'll use each of these for each of these. 2xz minus yz times a, which is negative 1 over radical 10, plus f sub y, which is this guy, times b, which is 0, plus this last one, x squared plus 2y cubed z minus xy times c, which is 3 over radical 10. So this middle term drops, and this is what we're left with. We could maybe just pull out that 1 over radical 10, keep things nice. Minus 2xz plus yz. Something like this. Now, what do you notice? What value do we get here? What type of value do we get here? Vector or scalar? Yeah. Well, there's still x's, y's, and z's floating around. So I can see how you might think it's a vector. But once I put in the coordinates of where I'm at, right, on the surface, this is going to all add up to get me a scalar value, right? It's going to give me the rate of change, right? The rate of change in the height, let's say, even though this is three-dimensional already. But it's the rate of change of f with respect to x, y, and z. So this will give me a scalar value. Okay. So that's important to note. And what's interesting is that this gives me the directional derivative at each point x, y, z. So what is this like? What does this really mean to you, this particular equation at the end? Who could just tell us in your own words what this thing does for us? Yeah. So, I mean, it's our first exposure to it. But if we think about this here, and again, this extends to not even just three-dimensional, but n-dimensional. What this tells us is that at any point xyz on the surface, what the rate of change is in the function in the direction of u, right? And so it's like we have this little vector, like a measuring stick, as we go around, acting as like our temporary axis where we're measuring the rate of change at every x, y, and z. And so now if you have a point on the surface, you'll be able to get that rate of change, right? So this would work for any triplet x, y, z. Okay, but it's all measuring how much it's changing in the u direction, right? Okay. So it's important to note that these few things. You check that you have a unit vector, and you can quickly make one if you don't. Understanding what this is, understanding that it's a scalar quantity, because the next point here is to unpack or explore this expression right here. So I'll ask you, does this look familiar at all or ring any bells? Not necessarily the symbols themselves, but how this is arranged. What does this look like to you? Something we've done a lot of involving vectors. So what was what was it that we did when we had a bunch of components and then we added them up, right? Multiplied them and then added them up. What was that? Doesn't it look like that? What was that called again?
Dot product?
Dot product. That's exactly right. Looks like a dot product. It looks like we just took a dot product and ended here, right? And so remember that what? A times B was A1 B1 plus A2 B2. I mean, you all know the dot product at this point. So yeah, but it looks like this dot product between two vectors that we don't know. Well, we know one of them, right? What is one of the vectors that it looks like it was dot producted? That's not a word, but that was a part of this dot product.
U.
Yeah, U is A, B, C, right? Our unit vector has these components. So it looks like we'll do A, B, C here. It was dotted with that, and then from this other vector that must have had components of the partial derivatives. So it looks like something was dotted with U. Well, what is this vector that has components of the partial derivatives of f? This is what we call the gradient. It's a vector that has the components of the partial derivatives of the function. And this has some interesting properties that aren't intuitive, are super helpful, and seem to kind of permeate and go into all these different nooks and crannies of vector calculus. And so we call it the gradient, and we use this del or Nambla symbol, this upside down triangle, to represent this. Okay, so this looks like here then the gradient of f dotted with u. And what was this whole thing equal to begin with when we started with this? This was the derivative in the direction of u of f of xyz, right? And so this is a really nice result to have. And it ties back to the comment from the beginning of maybe this has to do with an angle, right? Because what does a dot product do? It helps us either utilize the fact that we have an angle or bypass the fact that we don't have the angle between the two vectors, right? And still be able to compute this product. Okay, so this is the gradient. And so we'll use this quickly to see its helpfulness in this type of example. Find the derivative in the direction. For this function. z ln x squared plus y squared at the point -1, 1, 0 in the direction of 2, 1, 1. So we're looking for the rate of change in a given direction. We got to make sure that what is true about our direction vector need to make sure it's a unit vector, right? Need to make sure it's a unit vector. So we got to drive that magnitude to 1 if it doesn't have magnitude 1. This one does not, right? So we know we could take u to be v divided by its magnitude. Its magnitude is radical 6. Which is what? 2 over radical 6, 1 over radical 6, 1 over radical 6. So the derivative in the direction of u by this last result here is given by the gradient of f dotted with that vector. So we really just need the gradient of f. So we'll look at our function here. Take the derivative with respect to x. Well, we've got an ln and a chain rule. Z and y are constant. So this is what? 2xz over x squared plus y squared. Partial with respect to y is similar thinking. Derivative with respect to z, this is really linear with respect to z, so it's just the natural log of. So the gradient of f is given by this vector at each x, y, z. So, but we're curious about it being about this value at this point. All right, so we're looking for the gradient of f at -1, 1, 0. Well, if z is 0, that means these two terms here and here are both 0. X and y are -1 and 1. We square them and add them, that's ln of 2. So that's not too bad. So now we're talking about the dot product of the gradient of f at this point, which is this guy, with u, which is this guy, which is pretty easy to compute. All right, because we get 0 times 2 over radical 6 plus 0 times 1 over radical 6 plus ln 2 times 1 over radical 6. So we should just get ln 2 over radical 6. Again, it's a scalar quantity because it was a dot product. It's telling you a rate of change, the directional derivative. The gradient itself, though, is a vector. And I'll say this a couple times to try to drive it home. that it's a vector with the same dimensions as the input space, right? If you can think about f of x, y, z as being four-dimensional because it's got 3 dimensions on the input and 1 on the output, right? The gradient is a 3-dimensional vector. Okay, so it lives in the input space. That's important to make note of. So using it in this context to compute a directional derivative, super helpful. It's just dot the gradient with the unit vector that you're pointing toward. So the other way that this is used then, since it's tied to the dot product, and the dot product has just so many nice properties to it, that it allows us to maximize the directional derivative. And what do I mean by that? Well, if we notice that this is the directional derivative, right? Let me scoot this back. The derivative in the direction of u of our function, I'll just say f for now, so we can leave it, coordinate unspecific, general. It's a dot product of gradient with u. What was that nice theorem about the dot product? That it connected the components to the angle between them, right, based on the magnitude. So I called this like a directional multiplication back then. That was partly to foreshadow this here. The dot product is greater when what is true about the two vectors?
The angle between them is less, I believe.
Yeah, when they're sitting on top of each other, right, the dot product has a 0 angle, and so the dot product is maximized, right? And as they go to orthogonal, dot product turns to 0, right? So the bigger it is, and the more positive it is, that means that they're closer together. They're pointing in the same direction, and vice versa. So that theorem was that the dot product is equal to the magnitudes scalar multiplied to each other times the cosine of the angle between them. But we already know the magnitude of u, right? What's the magnitude of u?
One.
Yeah, it's 1. Use a unit vector. So that magnitude's 1, so we can feel free to not write that anymore. So this is really the magnitude of the gradient times the cosine of theta. So what does this say to us? Well, this says that the derivative in the direction of u depends on the magnitude of f times the cosine of the angle between the two. And so if they're pointing in the same direction, what's the cosine of the angle?
Zero.
Yeah. If they point in the same direction, cosine theta equals 1. That's the highest value it can achieve, right? So this is the maximal amount of change. So that tells us that the gradient of f gives the direction of the steepest change. Of f. That's kind of remarkable. So, I don't think that there's a straight line that you can draw between making a vector that has all the partial derivatives at each point and then saying, actually, this vector is pointing in the direction of the maximal change for the surface, right, for that function f. But that turns out to be the case. This has to be the case. So the gradient is the direction of the steepest change in f, meaning if you head in that direction, that's where the function is changing the fastest. The function's value is changing the fastest. All right, so let's put this to work. So find the directions in which the function f of xy equals x squared over 2 plus y squared over 2. We'll say first increases most rapidly at the point 1, 1. So again, a way you could think about this is I'm on a hillside, right, on the surface, z equals f of xy, so your coordinates are on the plane, then your height, and you'd look at which is the steepest way I could climb from here. And that's kind of like a nice way to remember what the gradient is, right? The gradient is the path of steepest descent. So how would I find the path of the steepest ascent here? Well, that's the gradient, so we're going to just go ahead and find that vector. All right, so for this surface in general, this is x, y, right? 2x over 2 and 2y over 2. And so at this point, 1, 1, then, we can say, some u equals, and this isn't a unit vector, so maybe let's just say v. Or equals I plus j, either, is the direction of maximum change. You could ask, too, how fast is it changing there? And that would be the magnitude of the gradient, right? So how about the direction in which it decreases most rapidly? At 1, 1. Well, it's just going to be the opposite direction, right? If it's the steepest in this direction, the steepest positive change, the opposite is going to be the steepest in the negative direction. Okay, so it's the opposite of that vector. How about where the change is 0? How would we find where there's the direction of 0 change? Like we'd be on a plateau if we moved in this direction, right? There'd be no change in z.
Would you have to cross it with the normal vector?
Cross it with the normal vector. Why? What would that get us?
It would give us like a sideways, it would give us a line that's like orthogonal, right?
Right. So that would work out. You would have to do a bit of work to first get the normal vector, right, and then cross it. There's another way to get there that's a little simpler and not use cross product, but we could use the dot product. When the dot product of two vectors is 0, what do you know?
Oh, then it just is orthogonal.
Yeah, it's orthogonal if the dot product of two vectors is 0. And to be orthogonal to the gradient of f, that means you have 0 change, right? That's the direction of 0 change based on this up here, right? If the angle is 90, then the derivative in that direction is 0. So we're looking for a vector. Need direction that is orthogonal to gradient of f. So I'm not going to work this out with you totally because it is, I want you guys to do this on your own after class, but essentially we dot this with some unknown vector u, set it equal to 0. Well, hey, that tells me that, the partial with respect to x times u1 plus the partial with respect to y times u2 equals 0. And then we can go in here, make some substitutions and solve. Should end up with something like this. But I'll say, you try this. There's multiple ways to tackle this. I'd say this is probably, especially with a two-dimensional vector, this would be the way to go. Couple notes here. I've said this verbally. But to see it sketched out even in a rough way. Let's say I've got some surface z equals f of xy. And this is like over the xy plane. Let's say I'm at some point here that's projected up to the surface, or on the surface projected down to the plane. It's like this vector here. I'm making it huge so you can see it. This vector here, this is the gradient of f. It lives in 2 dimensions, and it's telling you the direction to go for the steepest ascent. Does that make sense? It's on the map. It's a vector on the map. So it's a dimension down from your output space. So, and then, how fast it's changing right here at this point. That length from here to here, that magnitude is the magnitude of f. Magnitude of the gradient of f. but the direction, this lives in 2D for a 3D function. And again, we're going to have to start becoming clear spoken about input space, output space, and what we mean by how many dimensions, because, you can have a two-dimensional function in the 3 space, right? It just lives in the plane. It's still, a 3-dimensional function. So we're going to be clear about that. But what this also means, and this is a nice point, since playing with level curves and level surfaces is typically easier, more economical to do than to graph these things in 3D or beyond and try to make sense of them. Since the gradient of f is the direction of maximal change, it is normal to the level curves or surfaces. That's going to take some thinking. But to give you an intuitive sense of this, I have one graph I want to show you. Maybe not. Yeah, right here. That's not right. There you go. So, looking at a contour map of streams in a valley or in a mountainous region. You notice here, these are the streams with the 2 dots and the long segments here. What do you notice about them running through the contour lines? So this is the different elevations, right? Kind of like you've sent level slices through the surface. The angle that they're forming with each of these level curves is 90 degrees. Right? Why does that make sense? The stream is going to find its way down the path of steepest descent. Right? And in the same way, it's drawing the path of steepest ascent, going up. So what we're saying here is that the gradient as a vector is always going to point in this direction. It's going to point normal to the level curves. It's finding the path of steepest ascent. So that has to be, right, if you think about, if I'm standing on the edge where it's, 300 feet or whatever this is, what is the fastest way to change? Well, it's not going to be in this direction or that direction or this direction. It's going to be 90 degrees to the curve, right? That direction up or down will be normal to that level. So hopefully that makes sense. This is in the notes if you want to zoom in on this a little bit better. And pop back. But the gradient is the direction of maximal change, so it has to be normal to the level curves. And not just level curves, but level surfaces. So I'll sketch a little thing here just for our notes, but if we have something like this contour map, what the gradient does is it gives us at each point x, y, z And obviously it does this at every point, so we can't draw them all. And then this would be, if this was like a valley in the middle, let's say this was, 10, 15, 20 feet. At each point, it's assigning this little vector, okay? And that vector is normal to the contours. Okay, normal to those level curves. And if you think about it now in 3D, we had a three-dimensional surface, a level surface, which means I really have this four-dimensional function, right? Think for a moment. I have some function f of x, y, z. So it might be like a, ellipsoid or something like this. This is my input space, and then it's telling me what the temperature or something about, it's assigning a value to each of these. So it's really a four-dimensional function. But these level surfaces, if I let them be equal to k, I might have, some shells like this. And so the gradient is going to find the normal vector away from these level shells as well. If you think about, if this was, this was like k equals 1, here's k equals 2. Think about if you're on the shell of the level surface of this thing at k equals 1, it forms this ellipsoid, and the next one at k equals 2 is out here. What's the fastest way to get to the next level? It's out, right? It's out, it's normal to the surface that you're on. So you can think about those like Russian nesting dolls, right? If that's your input space, what's the fastest way to get from one to the next? Well, if you're on the surface of one, directly out normal to the surface that you're on. So that's what the gradient tells you at each point, is the direction of maximal change. So for a 3D like this, it's out. On a 2D level surface or curve like this, it's 90 degrees to the level curve. So what's nice about that is, since that's the case, we can get the normal at any level surface. So that means we can get a tangent plane just by using the gradient, as long as we kind of pretend to go up a dimension with a three-dimensional surface, and then we use the gradient in 3D. And that might not make any sense, and that's okay. But I'll show you how we put it into practice, and I think after using it, you'll know what I'm talking about. So this is something we've already done, find the tangent plane. But we'll show you a different way to get there. So find the tangent plane to this ellipsoid. Bless you. Crazy dogs. So what is this? This is a 3D surface but we can think about it from one dimension up. Think about this as a level surface for some big f of x, y, z equals k, where k equals 3. So instead of thinking about it as its own function, we can say, hey, maybe you're this level surface to some 4-dimensional function. So we'll call big f of x, y, z this function. And then we can use the gradient to find the tangent plane here. Right? Because if you remember, the tangent plane is what? It's the partial derivatives form the normal vector, right? When you zoom in close enough. We don't need to jot that down. So this would be the tangent plane. So then we can find each of these. Pretty easily. Right? Holding the other two constant means these partials are going to be nice and easy. So this will be, what, x over 2. F sub y is 2y. F sub z is 2z over 9. And then at the point negative 2, 1, 3, negative 3. Becomes negative 1, 2, negative 6 over 9, negative 2/3. So if we zoom in on this thing, x plus 2 plus 2 y minus 1 minus 2/3 z plus 3 all equals 0. Is the tangent plane to the above function at point P. And we know this is normal to the surface. Right? Because these components here are the components of the normal vector for the tangent plane. So where this just kisses this surface, that direction, which is the direction of the gradient, is the direction outward. So again, to kind of sketch what we just did, let's see, what point were we at? Negative 2, 1, 3. Negative 2, 1, negative 3. So we're like down here. So this is our quadric surface, x squared over, what was it? So that was this structure. But what we did was we said, well, let's pretend like this is a level surface for a function that's in a higher dimension. What we can do with that is use the gradient, which lives in 3D. The gradient tells us, oh, not that way. The gradient tells us a vector that's pointing outward. And then from there, we can generate the tangent plane that's just kissing at this point. So it forms 90 degrees with the surface itself. And we can do that at any point, obviously. That's a pretty nice application of this thing. And a pretty nice idea in general on its own to be able to think of a given surface as being some level surface from a higher dimension, right? We haven't done that yet. So in general, yeah, you have that. Okay, so the key points here. There's a lot of ways to think about the gradient. What were some of the ones that we named? The gradient represents if you had to tell somebody who was never going to take Calc 3 what the gradient means to them, what it means to you.
Direction of steepest change.
That's one. Direction of steepest change or maximal change in F. It's normal to level surfaces of F. Great. Oh, and I had some in the chat too. Yes, direction of maximal change. Absolutely. What else?
Its components are the partial derivatives.
Mm-hmm. Of the input space, right? Which means that it lives in the input space. We just saw that, right? Because we were able to take a 3D surface, but pretend that we were in the input space for some 4-dimensional function, and then use the gradient here, right, to find the normal vector and then the tangent plane. What is it? So I just had a question. What does it mean to be normal in this context? Normal is another word for orthogonal or perpendicular. We'll use it outside of the 2D sense. So to be normal to a surface is to form a 90-degree angle with it. So you can think about also, if you have the tangent vector, that's telling you the direction that the surface is moving in. You're forming a 90-degree angle with that tangent vector. Right. So yeah, it's perpendicular to contour curves and surfaces. Awesome. And we know that it's related to the directional derivative through this dot product, right? The derivative in a given direction is the dot with the gradient and that direction. Okay. So the input space is the xy plane. I had another question. Yes. For not for this one that we did, but for this one here. Here's a function where the input space is the xy plane. And where this function resides, right, is really in R3. So the output is the 3 space, and the input is the 2 space. So the gradient lives in the 2 space. It's a 2-dimensional vector, but the surface itself is 3 dimensions. And you could see, if we took level surfaces here of this paraboloid I drew, at any one of these level curves, the gradient del f would be normal to those curves. All right. So let me see. I think I had one more thing, but we're approaching time. Yeah. There are some cool proofs I was going to show you about the gradient, but I really think you guys could hack these on your own. Number 37 in the exercises. It'd be worth it, especially for the math majors, to punch through that and see how the operations work together. But it is totally gravy at this point, not necessary. But I will stop there. Do we have questions about any of these examples or ideas summarized today? Okay. Sounds good. Well, have fun. Enjoy the weather. Get out there. Live your lives. And we will see you next time.